Okay, so I hope everybody can see this, and I hope that you can hear me. So, okay, let's put this away. So thank you, Katie, for the introduction, and thank you to everyone for attending this webinar. So not only is this a webinar, but this is my PhD colloquium. So as Katie mentioned, I am a PhD student at Leiden Observatory in the Netherlands, and my specialty is on the synthesis of interstellar ice analogs. So in space, the temperatures are very low, so there's an abundance of ice. It's well recognized that UV photons from the star provides energy to drive a lot of the chemistry. Well, I'm going to highlight here that you can also form an assortment of astrochemically and astrobiologically relevant molecules at the low temperature of 10 Kelvin without energetic particles. And that's something that is not as well recognized. Okay. So one of the earliest stages of the star formation cycle is the dense cloud stage. So at densities of about 10 to the 4th, external UV photons cannot really penetrate through the cloud and also causes the temperature to drop to about 10 to 20 Kelvin. From these conditions, it would seem that there isn't that much activity going on in these clouds. However, observations show that complex organic molecules are formed in these clouds and can be made on dust grains. For example, signatures of methylformate, acetaldehyde, and ethanone have been detected in the torus molecular cloud. These species that are formed in the ice can then potentially be transferred to the next stages of star formation and or influence the chemistry in those stages. So some of the big questions that we still have, for example, are when these molecules are released into the gas phase during the warm-up period, do they participate in further reactions? What fraction of these molecules is inherited by the protoplanetary disk? And an even more fundamental question, are these molecules essential for chemistry on the early Earth? So if we want to better understand our origins, it's important to investigate the formation of molecules in interstellar clouds that we may have potentially inherited. So from the combination of observations, laboratory experiments, and computational simulations, we know that the dense cloud stage is further broken up into phases, which are largely dependent on the extinction or cloud depth. And in these phases, different types of ice chemistry occur. So at low visual extinctions or towards the edge of the cloud, water is the predominant ice and is formed starting from atomic H and atomic O. Solid state experiments have shown that water is efficiently formed on cold surfaces and that quantum tunneling is an influential aspect. As you go deeper into the cloud, more gas phase CO accretes onto these water-rich ices. The CO ice then gets hydrogenated to form formaldehyde and ultimately methanol. So the solid state pathway to methanol formation is found to be the dominating route to interstellar methanol. So because of this layering effect, there are two distinct types of chemistry that can lead to two distinct formation pathways of simple and complex organic molecules. So in the water-rich ice phase, more atomic species are available because of the relatively low density, and also carbon is not fully locked up in CO. As the density increases, more diatomics become available, and also more of the carbon is now locked up in CO. So in Leiden, in the laboratory for astrophysics, we try to simulate these two different types of chemistry in a systematic way in order to better understand the simple and complex organic molecule reaction networks in these two phases. And then from there, these molecules can be searched for by radio telescopes such as ALMA or directly in the ice with the James Webb Space Telescope. So the way we do this is through the utilization and constant modification of an ultra-high vacuum setup called SURFRESIDE. So this stands for Surface Reaction Simulation Device. So this setup allows us to study non-energetic processes at the low temperature of 10 Kelvin. And here, non-energetic refers to a radical-induced process that does not involve energetic particles such as UV photons or electrons, for example. So this non-energetic process is what we expect to be one of the more important processes to how simple and complex organic molecules are formed in these cold, dark, and particularly in these dense clouds. So we have a newly installed atomic carbon source, and the way this works is that we have a tantalum tube filled with carbon powder. This tube gets heated and carbon sublimes and reacts with tantalum to form tantalum carbide. So this essentially breaks apart molecular carbon into atomic carbon, and then the atomic carbon continues to diffuse through the tantalum and into the gas phase. We have a hydrogen atom beam source that produces hydrogen atoms by thermally cracking hydrogen molecules. We also have a microwave atom beam source that allows us to produce not only hydrogen atoms, but also nitrogen and oxygen atoms. We have two independent dosing lines that are turbomolecularly pumped. Cryostat is used to cool and heat the sample, which is where the ices are grown. And all the data is recorded by a quadrupole mass spectrometer and a Fourier transform infrared spectrometer. So the two techniques that I use are temperature programmed desorption, also known as TPD, and reflection absorption infrared spectroscopy, also known as RARES. So with TPD, I'm able to measure the mass of the desorbing species as a function of temperature. Since molecules have characteristic desorption temperatures, this is one way that we're able to identify the species formed. So, as the molecules enter the QMS, they're bombarded by 70 eV electrons, which can then fragment the molecule. This fragmentation pattern is then a fingerprint of the molecule formed. So for example, with water, we can find its fragmentation pattern in the NIST database, which is a very helpful database, especially if the sample is not available to you. So you can see that the most abundant fragment of water is the mass to charge value of 18. After that is the OH ion, which has the mass to charge value of 17. And then you can see that there are also other minor fragments, all of which contribute to the fingerprint of water. With RARES, I'm able to get the vibrational signature of the species that I form in the ice. So the vibrational spectrum can be recorded as a function of temperature, and then that can be linked to the TPD data. So now I'm actually going to discuss the science that I did these past 4 years. So overall, I studied the formation of simple and complex organic molecules in the water-rich and CO-rich ice phases. So the first 2 chapters focus on, the first 3 chapters focus on methane and methanol, and they're actually all related to each other. So the first 2 chapters are experimental studies, and the 5th chapter is an ice observation study. And then the last 3 chapters are predominantly experimental investigations on the formation of simple astrochemically relevant molecules to more astrobiologically relevant species. All right, so chapter 3 is on the study of the formation of methane ice. And this one is quite exciting for myself because this was recently published in Nature Astronomy. So the most abundant ices that have been detected towards young stellar objects are shown here. So in this figure, so the most abundant one is water, and experimental investigations support its formation from atomic O and H. CO2 is formed from CO plus OH. So CO and OH make the HOCO intermediate, so HOCO, and then that breaks apart to CO2. CO is a gas-based species. Methanol is formed from the hydrogenation of CO ice, and ammonia is formed from the hydrogenation of N. But what about methane? Observational constraints show that methane should be formed from the hydrogenation of C in the water-rich ice phase. But to date, this has not been experimentally proven. So how do we know that this can happen? So the closest experiments that have been performed were reported in 1979 and 1998. Although these laboratory experiments helped pioneer the field of laboratory astrochemistry, they were performed under water-poor conditions and also did not start from a beam of ground state atomic carbon in which the fluxes were calibrated for. So why hasn't the solid state formation of methane, starting from atomic C and H in a water-rich ice, been pursued? Especially since methane is one of the most abundant ices to be detected, you would think that, well, this would have been a priority. Well, this is because simulating carbon atom chemistry in realistic interstellar ice analogs is technically challenging. To do this, you would need to couple a carbon atom source to an ultra-high vacuum setup, which can be, well, quite risky. So for example, atomic carbon essentially has a sticking coefficient of unity at room temperature. So you can imagine if the carbon atoms to the blades of the turbomolecular pump, this will cause a mass imbalance and can potentially destroy the pump. Carbon can also short circuit electronics. This is a true story. This is not my true story, but this is a true story. And if the entire beam is not focused, you can easily have unwanted coatings of carbon. But anyways, we were able to get through these obstacles, and the first science project was to actually form methane starting from atomic C and H. So two different types of experiments were performed, one without water and one with water. Since methane is observationally constrained to be formed also when water ice is formed, there may have been a short period when methane was formed just before water ice. So we wanted to see if that was experimentally possible. And then, of course, we wanted to see if methane could be formed in a water-rich ice as it should be in space. In the water experiment, it's important to note that water was deposited rather than being formed, and that's because we just wanted to disentangle the methane formation route. So water deposition is not meant to simulate the accretion of water on interstellar dust grains, but rather used as an experimental tool. The hydrogen flux is an order of magnitude higher than the carbon flux, which is meant to represent the overabundance of hydrogen compared to carbon in interstellar clouds. And a methane to water ratio of 10% was chosen as this value has been measured towards some low mass young stellar objects. So these panels show the rare spectra of the CH bending mode of methane, which is the most intense vibrational mode of methane. So these were recorded after 720, 1080, and 1440 seconds of deposition in the two different experiments. So you can see that, that it didn't take that long to acquire what I consider as good looking spectra. So I was very happy with the signal to noise. And then for extra confirmation of methane formation, the left panel shows the isotopic shift of CD4 when D is substituted for H, and the right panel shows the presence of the weaker CH stretching mode of methane. So it's quite clear that in the water-rich ice experiment, more methane is actually formed. So under our experimental conditions, the rate of formation is about twice as high compared to the experiment without water. So one of the concerns we had was whether water would block C and H from meeting each other in the ice. To some extent, water probably does block C and H. However, this seems to be overpowered by the fact that water increases the resonance time of hydrogen in the ice. And this may be partially due to the increase in the sticking coefficient and binding energy of hydrogen. And also water provides a larger surface area for hydrogen to absorb to. So there's actually more hydrogen available to react with carbon than if water wasn't present. So after a series of control experiments, which are not discussed here, we find that this is the expected dominating mechanism to methane formation in our experiments, which supports observational studies that methane should be formed in the water-rich ice phase in interstellar clouds. Now, in the interstellar medium, the methane-water correlation will be set by the availability of the simultaneous accretion of C, H, and O. But because there is more water than methane, it should be taken account into models that C and H are expected to react in the growing polar ice. All right, so to put this work into a larger context, radiation chemistry in the gas phase is needed to provide ample C and an O atoms. These atoms accrete and react to form the simple hydrides. These simple molecules can then break apart and recombine to form larger species, or they can remain intact and be transferred to the next stages of star formation. So for example, Titan's atmosphere is thought to have inherited some of its methane from the interstellar medium. Taking into account the C atom channel in addition to the N and O atom channels will be important to put the present work into a cosmochemical context. And this is especially timely with the JWST. Well, there are a lot of projects that are especially timely with the JWST, but the fact is that methane is best observed with space-based observatories. So the JWST will be a desired facility to detect methane ice particularly since high sensitivity is needed if you want to detect methane in quiescent clouds. All right, so the next two chapters now focus on methanol formation, particularly how it's formed and when it's formed. A common theme between the two studies is, can methanol be formed from methane? If so, then that also affects the methanol ice formation threshold, which describes when methanol ice is initially formed. So methanol, which is also the simplest COM, can be formed by this reaction chain up here. So methyl and methane are representative precursors that are formed in the water-rich ice phase, most likely through the accretion of atomic carbon and hydrogen. This is in parallel to the formation of water ice through the accretion of atomic oxygen and hydrogen, as mentioned before. With that being said, OH radicals are also representative precursors that are formed in the water-rich ice phase, also through the accretion of atomic oxygen and hydrogen, and also from the photodissociation of water. Under our experimental conditions, it is difficult to create OH radicals by atomic oxygen and hydrogen. So instead, we make OH radicals by H plus O2, which also gives the side product H2O2, as found in a number of works. However, this does not affect the main conclusion of this study, which is that methanol is formed from methane plus OH. So I did a number of control experiments to confirm that I did form methanol. So this is the rare spectrum of the final ice, and you can see the CO stretching mode of methanol at 1001 wave numbers. And to confirm that that little bump is a CO stretching mode, I looked at the isotopic shift using 13C and 18O, so you can see the corresponding redshift in the infrared data. The desorption temperature and profile seen in the experiment are similar to that of the pure sample. So this 2 Kelvin shift is due to species like water, which has a higher binding energy than methanol. The QMS fragmentation pattern also matches nicely between the isotope experiments and to that of the pure sample. So the this red line here is the average relative intensity between the isotopes. So you want to compare that to the intensity of the pure sample. So you can see that this is actually within the instrument error of 4%. And then finally, you can see that the methanol feature disappears between 145 and 155 Kelvin, which is the range at which methanol desorbs. So from here, it's concluded that methanol is formed from methane plus OH. By comparing the methanol abundances, we find that the methane plus OH pathway is about 20 times less efficient than the CO plus H pathway. However, this does not mean that this is not astrochemically relevant. So there's a review paper published by Advin Bogert and co-authors, and in one of the figures, he shows the detections of methanol ice and the upper limits of methanol ice as a function of the visual extinction. And what's puzzling about this is that the upper limits are primarily below the detections, even at high extinction. So what we think is happening is that there may be less efficient alternative reaction pathways to forming methanol in some of these clouds, such as methane plus OH. However, more data points are warranted, especially at the low visual extinctions, as you can see that the sample size is not that significant. So that leads me to the follow-up observation project, where I actually tried to obtain more data points. I did obtain more data points, but they are mostly upper limits. So since this work is not published, I'm just going to very briefly touch on it. So the two telescopes that were used were IRTF SPECS and Keck with NERSPEC. So the goals of this project were to, 1, obtain more data points, and 2, increase the sensitivity of previously published and new data. So photospheric line contamination from the background star can lead to noisy data. So I created a script in Python to remove these lines. 41 stars behind dense clouds and cores were sampled, and a range of visual extinctions was probed. So the visual extinction can be regarded as the cloud depth. So methane and water are formed at low visual extinctions at the edge of the cloud, and methanol is currently constrained to be initially formed deeper into the cloud at high AV. And my hypothesis is that methanol should also be formed when methane is formed. So it should be formed earlier than we expected. So I'll first show the results of the photospheric line correction. So using template spectra of unreddened stars, I was able to subtract out the photospheric line contamination in the region where methanol signature is probed. The problem is that there's an ammonia hydrate feature right next to the methanol feature in many of my data. So that's something that we're still trying to resolve. And then for reference of what a methanol detection looks like, you can, so I stacked the data and you can see that there's a pronounced feature at 3.537 micrometers that needs to be apparent in order to securely identify a methanol signature. So the top panel shows my 1 detection of methanol ice, which brings the total to 8 detections of methanol ice in quiescent clouds, or so towards background stars. So we definitely could have more detections. And then the bottom panel shows that I was not able to confirm a previous methanol ice detection with or without photospheric line correction. This detection did have the lowest column density out of the 8 detections, so maybe the choice of baseline is the reason for this discrepancy. And then finally, after 34 upper limits shown in the open blue circles, you can see that the trend still holds, that there's a big discrepancy between the detections and upper limits at high visual exclusion. And it's quite obvious that with just 1 more detection included, the error bar on the methanol formation threshold didn't get any better. So there's still no observational evidence that methanol is also formed from methane, but it's also clear that more detections are needed to constrain the methanol ice formation threshold. So this is still a developing story. All right, so back to the lab. So now I'm going to discuss chapter 6, which discusses an alternative way to form formic acid and CO2 ice, which is starting from formaldehyde. So both formic acid and CO2 have been detected in various environments across space. So if the identification of solid state formic acid is correct, it has an abundance relative to water ice of less than 0.5 to up to 6% towards dense clouds and low and high mass young stellar objects. And CO2 ice has a CO2 to water abundance ratio of 15 to 35%. A number of laboratory experiments have shown that formic acid and CO2 can be formed by both energetic and non-energetic processing. And in a number of those studies, it's been found that formic acid and CO2 are simultaneously formed and share common formation pathways. Although observations show that CO2 ice is predominantly formed in a water-rich ice, it's also been found that CO2 ice exists in a CO environment. So that's what we investigate here. Starting from formaldehyde, which is formed from the hydrogenation of CO ice, we show that formic acid and CO2 can be formed. So the formation pathways of these 2 species in our experiments are determined by the combination of the experimental data and data available from the literature. But this is a bit lengthy, so I'm just going to skip that for this talk. And then the astrophysical implications are discussed, namely that formic acid and CO2 can also be formed in the CO freeze-up stage. So the main reaction of this study is formaldehyde plus H plus O2, where H plus O2 is used to create the OH species that partially makes up formic acid. O2 also has some relevance here in that it's thought to be formed also with CO ice, which also goes in line with the higher availability of diatomics in the CO freeze-up stage. So the formation of formic acid is shown in the TPD data. Although formic acid desorbs at 142 Kelvin in its pure form, the literature shows that formic acid typically higher temperatures when mixed with less volatile species, which is what we see in the original and isotope experiments. And what's especially useful with these isotope experiments is that so formic acid has 2 oxygens, one which should belong to formaldehyde and one which should belong to O2. So if you see the correct isotopic shift in the mass spectrum, then that's even extra confirmation that what you're detecting is formic acid. So for example, by incorporation of 18 oxygen, so on the bottom left panel, we should see the desorption signal of mass to charge 48, which represents only 1 oxygen being isotopically enhanced, which is what we see in the TPD data. And then for the infrared signature of formic acid, it's not as straightforward to detect because its strongest features overlap with that of formaldehyde. So what we did was perform a multiple linear regression or MLR analysis, which does not provide conclusive evidence, but rather provides complementary results to the TPD data. So in an MLR analysis, the relationship between the dependent variable and independent variables is determined. So in our case, the dependent variable is the formaldehyde plus H plus O2 spectrum, and the independent variables are the spectra of the components of that spectrum, which are formaldehyde, oxygen, water, formic acid, and hydrogen peroxide, where hydrogen peroxide is a product of H plus O2. So, pointer option. Oh yeah. You can see that if you don't include formic acid in the MLR spectrum, the shoulder at 1740 wave numbers disappears. If formic acid is included in the MLR, then the shoulder matches with the shoulder seen in the original spectrum. So the shoulder is expected to be representative of a blue shifted C double bond O stretching mode of formic acid. And then the formation of CO2, it's very straightforward. So we see its intrinsic desorption at 80 Kelvin in 2 different isotope experiments, as well as its expected isotopic shift in the infrared data. So in essence, formic acid and CO2 have the potential to be formed in the CO freeze-out stage starting from formaldehyde. This is quite interesting for the case of formic acid since it has not been securely detected. So hopefully this provides extra incentive to go look for it. So from an observer's point of view, it's likely that if you were to observe at extinctions where CO freezes out, the total column of formic acid should be higher than if you were to observe at extinctions below the CO freeze-out point. All right, so my last 2 chapters of my thesis, chapter 7 and 8, which are about the formation of more astrobiologically relevant molecules. So some years ago, our primary focus was on understanding the column formation route in the CO freeze-out stage. In the work by Koju Chuang and co-authors, he shows very nicely the CO plus H reaction network that is derived from the experimental findings. In the network, he finds that glycolaldehyde, ethylene glycol, and methyl formate can be formed. Now, if you wipe over and continue to bombard CO and H, you can form glycerol, which is a necessary ingredient for glycerophospholipids, which are what modern cell membranes are composed of. So the glycerophospholipid bilayer makes up the cell membrane, and then the glycerophospholipid itself has glycerol as the backbone. And then if you continue along this formation pathway, you could even form ribose, which is an essential component of RNA, for example. So yeah, I think this is super cool because you can form all these molecules at super low temperatures and without energetic particles. And potentially you could even form something very relevant to what's important to life. Now, if you add a hydrocarbon radical to the CO plus H reaction network, you can form 2 additional comps. So you can form propanol and an alcohol and propanol. So these are the 2 molecules that I studied. So propanol is of interest as it has already been detected in space, but its formation pathway is still unclear. And propanol is elusive in that it has not been detected. However, it is an astrobiologically relevant molecule in that it is a primary alcohol. So in today's life, cell membranes are primarily composed of glycerophospholipids, which, however, require enzymes to be formed. These enzymes were likely not available on the early Earth, so it's hypothesized that primitive cell membranes were partially formed by simple lipids, such as phenolipids, which can be composed of primary alcohol. So I'll first show the TPD results of the formation of propanol. So the most abundant fragment of propanol is the parent ion. So I search for the mass to charge value of 58 as well as the fragment 57 for extra confirmation. So in the acetylene plus CO plus H experiment, a peak desorption is shown at 125 Kelvin, which is also the peak desorption temperature of pure propanol. Because the peak desorption temperatures are the same between the 2 experiments, we have 1 confirmation that propanol is formed in the acetylene plus CO plus H experiment. And then for extra confirmation of propanol formation, I looked at the CO isotopes so that I could see the mass to charge shift at the desorption temperature of 125 Kelvin in the mass spectrum. So the relative intensity between mass to charge values of 57 and 58 in the pure propanol experiment is 33%, which is the average relative intensity found between 3 different experiments that contain 3 different isotopes of CO. So with these verifications, it's confirmed that propanol is formed in the acetylene plus CO plus H experiment. Propanol is derived from the hydrogenation of, or derived from propanol. But because of side products and also the limited abundance of propanol, we could not directly detect propanol in the acetylene plus CO plus H experiment. So to go around this, we deposited pure propanol and hydrogenated it, and indeed we see the signature of N-propanol. So using 4 mass to charge values, the TPD data shows the desorption of pure propanol at 125 Kelvin and the desorption of pure N-propanol at 155 Kelvin. In the propanol plus H experiment, we see 2 desorption peaks, one for propanol and one for newly formed N-propanol. When N-propanol is fragmented in the QMS, it can break apart into mass to charge values of 60, 59, 31, and 29. Their fragmentation pattern in the pure N-propanol experiment is shown here. So this pattern is nearly identical to the pattern found in the SAFE experiment. Therefore, it's concluded that N-propanol is formed from propanol plus H. There's also temperature-dependent infrared data, which is complementary and can be linked to the TPD data. So the CO stretching mode of N-propanol at 970 wave numbers is a relatively strong feature and also does not overlap with propanol features, which makes it a good candidate to look for in the propanol plus H infrared data. So you can see that this band disappears by 155 Kelvin, which is also the peak desorption temperature of pure N-propanol, making it very likely that this feature is representative of N-propanol. So by puzzling together the reaction products and activation barriers derived in this study and also from the literature, we're able to constrain the 2 most likely formation pathways of these species, which are the 2 displayed routes. So as you can see, the conversion of propanol to N-propanol has an activation barrier of 2620 Kelvin. Well, this represents the scenario where hydrogen is first added to the carbonyl carbon, then added to the oxygen. Another scenario could exist, which is that hydrogen is first abstracted from the carbonyl carbon, which has a lower activation barrier of 2560 Kelvin. Hydrogen is then added to the oxygen before it is added to the carbonyl carbon. So the conversion of propanol to N-propanol could have an even lower activation barrier than 2620 Kelvin. So from this work and also from the other studies on the CO plus H reaction network, we see that a number of COMs have the potential to be formed without the input of energetic particles at the low temperature of 10 Kelvin. And this includes the formation of propanol and N-propanol, where N-propanol is an astrobiologically relevant molecule. Although N-propanol is still elusive in the observational surveys, we recently investigated conformation in the water-rich ice phase. And because of the availability of the OH radical, we find that a number of alcohols have the potential to be formed during this phase, including N-propanol. So now I'm going to segue to conformation in the water-rich ice phase, where all of these COMs are alcoholic and form starting from propine. So N and I-propanol are detected in the experiments. N and I-propanol are tentatively detected in the experiments, but with the combination of the experimental data and computationally derived activation barriers, we find that propanol is formed in our experiments. And then finally, we have strictly tentative detections of 3 isomers of propane diol. And just a warning, there are a lot of tongue twisters coming up. But before I dive into the experimental results, I think it's useful to further expand on the link between alcohols and astrobiology. So as mentioned previously, glycerol is the backbone to which fatty acids are attached to in glycerophospholipids. Well, with other types of lipids, other alcohols can act as the backbone. So for example, sphingolipids use the amino alcohol sphingosine as the backbone instead of glycerol. And also waxes, which are simple lipids, contain these long chain alcohols. So it's important to, I think it's important to assess the fundamental nature of these big alcohols, which is to first understand how these small alcohols are formed. So the origin of cosmic carbon lies in the outflows of carbon-rich stars, as shown very nicely in this figure. And how carbon evolves into small and large hydrocarbons is still far from understood. So there's the bottom-up approach, which merges smaller precursors into larger species, and also the top-down approach. In this study, we just focus on the bottom-up approach. So from a bottom-up perspective, simple species like acetylene can polymerize to form polyions. To make it more complex, a methyl group can be added to form methyl polyacetylene. Such species can then accrete onto carbonaceous dust grains that were formed from the nucleation of PAHs. In this study, we just focused on the simplest representative of methyl polyacetylene, which is methyl acetylene, also known as propine. So propine has been detected in a number of regions in space, including towards a carbon-rich star, as we would expect. So as the carbonaceous grain that is coated with hydrocarbons makes its way deeper into the cloud, water ice starts to form, which means that OH radicals are available on the grain surface. And so it's the chemistry at the interface of the carbonaceous grain that is coated with hydrocarbons and the water-rich ice that we investigate in this study. So the precursor of the OH radicals involved is a hydrogen atom, so I first studied the hydrogenation of propine. So the triple bonded carbons can essentially be hydrogenated to a double bonded carbon to form propene, and then the double bonded carbons on propene can be hydrogenated to form propane. In the work by Kobayashi and Watanabe, it was shown that the 2-carbon equivalent acetylene can be hydrogenated to form ethene and ethane. So it's no surprise that propine can also be hydrogenated to form propene and propane. So this is the rare spectra of propine and propine plus H acquired at 10 Kelvin. And you can see that there are a number of propene and propane features that overlap with each other, but there are 2 distinct peaks, which are the C double bond C stretch of propene and the C single bond C stretch of propane. The TPD data provides additional proof for propene and propane formation. So the fragment with the highest relative intensity for propene is mass to charge 41, and for propane, it's mass to charge 29. So propane is known to desorb around 80 Kelvin, which is what we see here. But to distinguish between propene and propane desorptions, the effects of pi stacking come in. So since propene has a double bond, it has pi electrons, which are available to form bonds, whereas propane is saturated, and so the interactions between propane molecules are more weak. So we would expect to see propane desorb just before propene. And then you can see that there's some co-desorption of propane with propene, and that's likely due to the amorphous to crystalline phase transition of propine. So now I'm going to discuss the chemistry when the OH radicals are added to the reaction. So in 2 different isotope experiments, so one experiment with 16 oxygen and one experiment with 18 oxygen, we see the desorption of N-propanol at 163 Kelvin and the desorption of I-propanol at 160 Kelvin. The desorption temperature of pure I-propanol is around 150 Kelvin, but when trapped in a matrix with relatively less volatile species, the desorption temperature of I-propanol increases to around 160 Kelvin, which is the desorption temperature that we see in the experiment. And then for extra confirmation of N and I-propanol formation, the QMS fragmentation pattern of both species was measured in the normal experiment. So that's without isotopically enhanced oxygen, the isotope experiments, and the pure sample. And you can see that the QMS fragmentation pattern variation is within the instrument error. And a 1-to-1 abundance ratio of N-propanol to I-propanol was measured from the TPD data. All right, so N and I-propanol are expected products that are tentatively identified in the experimental data. And they're tentative because pure samples are not commercially available, as the propanols undergo ketoenol tautomerism at room temperature to primarily form propanol and acetone respectively. However, this work is supported by computational calculations, and by comparing the experimental and theoretical data, we find that propanol should be formed alongside propanol. So mass to charge values of 43, 57, and 58 can represent propanol, and their mass to charge shifts are also seen in the 1802 isotope experiment. Like that of NNI propanol, the isomers of propanol likely do not desorb at the same temperature, so we see two different desorption temperatures. And then the desorption temperature of around 155 Kelvin for propanol is between the desorption temperatures of propanol and propanol. And this is expected if you compare this to the desorption temperatures of acetaldehyde, phenyl alcohol, and ethanol, which are the two carbon counterparts. All right. So for the formation of 3 isomers of propanediol, we also have tentative detections. So propanols should be present in the ice, and they can be hydroxylated to form propanediols. So 1,2-propanediol is stable at room temperature, but 1,1 and 2,2 propanediols are not. So when 1,1 and 2,2 propanediols are released into the gas phase, they can decompose into propanol and acetone, respectively. So that's what we think we're seeing in the experiments. So propanediol has a desorption temperature of around 205 Kelvin, and we see peaks of acetone, propanol, and 1,2-propanediol at 207 Kelvin. So by puzzling together the experimental products and computationally derived activation barriers, we're able to construct a formation network that is most likely occurring in the experiment. I'm not going to discuss the computational calculations that were performed by my collaborator, Tanya Lamberts, here in Leiden, but rather I'm just going to give you her final results and my final results and how they come together to form a formation network. Since the barrier for hydrogen addition to the exterior carbon is lower than hydrogen addition to the interior carbon, hydrogen addition to the exterior carbon is the most likely pathway to propene and propane formation. Because of the much lower activation barrier, we find that OH addition is more likely than H addition to propine, only when OH is very close to propine and oriented in a favorable position for reaction. The 1-to-1 average abundance ratio of N-propanol to I-propanol from the experiments also matches nicely with the computational calculations. So Tanya also found that they should more or less have a similar abundance. And by the way, we figured this out independently first and then came together. And then you can see that in order to make propanols, we must make propenols. So propenols are products formed in our experiments. So you can see that these alcohols can potentially be formed in the water-rich ice phase. And since they're thought to be formed at the grain-ice interface, these alcohols can potentially be protected by the upper ice layers if they were to be delivered to the early Earth, for example. Now that we've performed experimental simulations of what molecules we expect to be formed in the water-rich and CO-rich ice phases, these molecules can be targets for ALMA and JWST observations. So for ALMA, the group of Avina Vendishik, they are looking for N-propanol. So I think the group of Jess Jorgensen had detected propanol before, and propanol is a precursor of propanol. So now we're looking for propanol in that same region. So that's towards the low mass protostar 16293. And then with JWST, hopefully I made a convincing case as to why we need to detect methane ice. And also, well, we just need more detections of methanol ice. And well, I'm not an expert in this, but I know that JWST has the capability of ice mapping. So I think it can probe like 100 background stars in one go. So that's 100 more data points. And right now we only have 8 detections. So yeah, so I'm really excited for the launch of the JWST. And then, of course, astrochemical modeling is desired to take into account the experimental, theoretical, and observational results to better understand the astrochemical relevance of the proposed reaction network. So I'm very fortunate that now this is actually happening. So my collaborators at NASA Goddard Space Flight Center, so that's Gwen DeFore, Stephen Charnley, and also Tanya Lamberts here in Leiden. They are creating an astrochemical model and taking into account all my results to see which ones are more or less astrochemically relevant. So I'm looking forward to the results that they get. And thank you very much. This is the summary of my PhD work this past 4 years. And yeah, I'm looking forward to any questions or comments that you may have. Thank you for the clapping. Let me grab some water. I don't see any questions. Maybe.
Donna, are you able to see a question from Alec Pauly?
I don't see it.
Okay. So I'll read his question. So from Alec Pauly, I hope I'm pronouncing that correctly. Thank you for the wonderful talk. I was wondering if you had any thoughts on the possibility of oxygen insertion reactions as another production route to form methanol on ice, potentially from electronically excited oxygen.
Yeah, so to form, sorry, it's oxygen insertion to form methanol. Is that correct? Or into
yes.
methanol?
Oxygen insertion reactions as another production route to form methanol on ice, potentially from electronically excited oxygen.
Yeah, so that's a very good question, and there is an experimental study that proves that. So it's the paper by Jennifer Berkner and Karin Oberg. So they actually show O∪D can be inserted into methane to form methanol. So that I think would be a good paper to look at. Oh, I think I actually am wait, there's a chat. Aha. Excellent, excellent, great job. Thank you, everybody. I appreciate it. Yeah, and if anyone has questions on like what it's like to be a PhD student in Leiden, I'm also really happy to talk about that as well. All right, so undergrad from India, can you elucidate the minimum number of nano-sized water droplets that could form ice crystals? Can you elucidate ice crystals? Nano-sized. You know what? I don't think I can. That's a tough question. That could form. So we basically put in water vapors into our system at very, very low pressures, and we can already detect ice, water ice with our mass spectrometer and also with the infrared. So you don't really need that much water to form ice crystals. All right, could the formation of clusters in methanol ice influence in these hydrogenations, since there would be more hydrogen? Could the formation of influence in these hydrogenations, since there would be clusters of methanol ice influence? Actually, I'm sorry. Could you maybe rephrase that, because I'm not sure exactly how to answer, or I think I just don't understand the question exactly to give you the best answer. Thank you. I'm just going to answer the next person's talk, or next person's question. So how is the work-life balance for PhDs? Very informative. So I have like Okay, sure. Leiden Observatory is watching me now, but I can honestly say, and anyone who knows me at Leiden, that I love the PhD here. I think the work-life balance is amazing. I'm from the US, so that's probably a big reason why I think the work-life balance is so great. There's a lot of holidays here. One thing that I really like about Leiden Observatory is that they really they really like for you to talk with each other and to collaborate. So a lot of times we take a lot of coffee breaks and we meet together and we just kind of informally talk. And those little conversations, those little informal conversations actually go a long way in your research and with forming networks and collaborations. And I just like that it's such a collaborative environment here. Yeah, and I think they're very respectful of your time. They don't want you to, like, you know, nobody comes into the observatory on Saturday. That's just ludicrous. So I really like that yeah, all I can say is the work-life balance is very, very good. And if you want more specific information, I'm happy to email you about more information about the work-life balance here. Okay. Could you please tell a detail about the carbon source? Yes. It's what's the detail? It's a bit stressful, the carbon source, but no, it's not that stressful. So the carbon source, we actually just my last paper I just published in Review of Scientific Instruments. So that actually has all the details of how we incorporated the carbon source into the current setup. So the reason why we need carbon source is because so we have the capability to study hydrogen, nitrogen, oxygen atom chemistry. But of course, there's carbon available in the universe, and carbon is very important, especially for understanding the signatures of life. So that's why we put in the carbon source. What's so tricky about carbon is that it's super sticky. So whatever it, like, under our working conditions, whatever it hits, it just sticks there and it doesn't go away. And I have used 2 turbo pumps that have died with my carbon source, and I don't know if it's because the turbo pumps are just not good quality or if the carbon source did that itself. So if there's one detail I can say about the carbon source is that it is very, it's sticky, yeah. But the good thing is you can have a very focused beam because, yeah, it doesn't really scatter away. The beam is pretty focused, so whatever it hits, it just sticks. So you don't have carbon like going all over your chamber, for example. Okay. Did you find any methanol signature while working on methane formation from CH in water? Good question. That is a very good question because that is what we are working on right now. Yeah, so when I did CH in water, yeah, I guess I'll say, so we saw formaldehyde and we saw methanol. And right now we're trying to understand why. And actually that's a paper that we're writing in collaboration with Tanya Lambert. So she's doing the calculations for that. Yeah, so yeah, methanol just seems to be everywhere. Yeah, I'm not sure why. Okay, we've observed the formation of clusters in methanol ices. Okay, and since we've observed N is 7, there would be long chains of methanol. Since that would mean more hydrogen, that excess could influence these hydrogenation process that you talked about. I'm sorry, Rodrigo. I'm still not understanding the question. I think this would be a better question to discuss offline. I'm gonna get note of your name and I'm gonna send you an email, and I hope that is okay with you, because I'd really like to understand the question better. And I'm sorry, I can't answer it right now. Okay. Thank you, Maria. Could you comment on the energy of the carbon atoms that are produced in your setup, or at least how do they compare to the energy of the N and O atoms? Another very good question. So the energy, okay, so we know so we measured the energy. So when the carbon atoms are released from the tantalum, we've recorded with the pyrometer the heat. And so that energy is actually about 2000, like 22 to 2400 Kelvin. So the carbon atoms are very hot. And actually, a lot of our atoms are very hot. But the difference, so when we produce nitrogen and oxygen atoms and hydrogen atoms, there's always a quartz tube at the end of the source, and the atoms will collisionally release their energy onto the tube. And we've done a lot of experiments showing that hydrogen thermally equilibrates to the temperature of the surface prior to a reaction. With carbon, we can't have a tube because the carbon just sticks. It will just stick to the tube. So right now, we're trying to better constrain the temperature of the carbon atoms in the ice. Right now, all we can do are barrierless reactions because that should not quantitatively affect the results. So for example, to form methane from C plus H, that's barrierless. So that's why it was kind of an exciting project, but also experimentally safe project, because I know that methane is going to be formed whether you have heat or not. So I guess the short answer is that we know the temperature in the gas phase, which is about 22 to 2400 Kelvin, but in the ice, we are still doing experiments trying to constrain at what temperature they are and if they thermally equilibrate to the temperature of the surface prior to reaction.
Okay, so since it's now noon or 6 p.m. or whatever time it is, wherever you guys are, I know we have a pretty international audience. I'm gonna go ahead and conclude this. So Donna, if you wouldn't mind stopping your screen share.
I think I stopped sharing.
Yeah. Okay, so big thank you again to Donna for the excellent talk, and of course our audience for joining us and asking thoughtful questions. It's really great to have you guys here every week, so thank you for coming.
And thank you, Katie.
Thanks. And then coming up next week, we have Dr. Stephanie Milam from NASA Goddard on Tuesday, and Dr. Paula Sivaraman from the Physical Research Laboratory on Thursday. So be sure to come and attend those talks. And we'll see you guys hopefully next week. Thank you again, everybody.